Okay, so let's start. It's my great pleasure to present you Mirna Džamonja. Mirna grew up in Yugoslavia, the country that does not exist anymore, but it existed when I was young, many years ago. And she left Yugoslavia in 1988 to do her master's and PhD at Wisconsin Madison. This was not long before this terrible war started in the Balkans. Mirna is a citizen of Bosnia and Herzegovina, Belgium, and UK. Currently, she is a professorial researcher at CNRS Université de Paris Cité. She is also an associate member of the Institute de la Philosophie des Sciences et la Technologie Université Panthéon-Sorbonne, which is Paris 1. And before, she was a professor at the University of East Anglia, Norwich. Her research is in mathematical logic, especially set theory, but she's particularly interested in connections to other fields of mathematics like philosophy and theoretical computer science. She published in set theory, model theory, set theoretical topology, measure theory, and combinatorics. Her results include methods of proving existence of some objects by forcing or proving that certain objects under certain assumptions do not exist. She has also published in philosophical logic and in history of mathematics. She is very active in building mathematical community. She was a founding member and president of the European Set Theory Society and chair of the Logic in Europe Committee of the Association of Symbolic Logic. And on top of mathematical papers, she's an author of 2 books, Fast Track to Forcing and Théorie des ensembles pour les philosophes. She promoted 17 PhD students. Okay, now Mirna, the Zoom is yours, please.
Thank you so much, Eva. Well, this wonderful introduction that you prepared on my behalf is, of course, very humbling. Thank you very much for the nice words that you have said. May I also tell you how honored I am to be invited to this conference and to meet you all, even in this way. I think that many things that Eva has mentioned about me can be said about her, because she is such an active mathematician with a wonderful list of publications, but at the same time, somebody who has involved herself in the mathematical community very much, including organizing this conference. And I think that this is the kind of approach that we have to build in our community, rather than being always obsessed only with publications, numbers, quotients, and so forth, things that we are judged for. Well, she does well on both of those things, of course, but I just wanted to emphasize how touched I am by the human aspect of this person. Now, let me go to my topic. I'm going to tell you things that I'm doing as part of a project that kind of is new for me. You've heard these things that I did during my life, and you know, when you come to a certain age, you have done many things in your life. So I love mathematics. I started doing mathematics, like many of you, I'm sure, from the days of mathematical competitions, and then I went and learned various subjects and was always fascinated by mathematical logic. Mathematical logic fascinated me because I feel that it is important to see sort of a big picture of what's inside of mathematics. So what are the common things that mathematicians do? And that is what mathematical logic is about. And in particular, set theory is about that because much of our mathematics can be formulated in terms of sets. And well, so this is something that has always fascinated me. But I've noticed at some point that this idea that we have in set theory of looking at big sets, big infinities, I will explain what I mean by that, is quite a nice idea. It is very interesting, and this is what I do my research on. But it has a sort of reflection on rather small objects, objects that are of interest to people doing theoretical computer science. So now let me just say a few words. I think you are mostly interested in mathematics and mathematical students, if I understand correctly. But still, you come from Poland, which is a biggest, I would say, perhaps, center for theoretical computer sciences, along with France. You have wonderful researchers doing this subject. So what are theoretical computer sciences? And why should we mathematicians be making connections with this subject? So in theoretical computer sciences, actually, people do many things, but the part of it that is mostly what I know and what I'm interested in has to do with modeling processes of computation. So rather than looking at some concrete computer with some concrete programming language, one looks at how to model what is a process of algorithmic computing. So it is a little bit like set theory, because in set theory, you rather than looking at some specific kind of objects in mathematics, you look at kind of jointly useful objects that exist in mathematics, and you try to make some theorems that then you can apply to concrete cases as you. So theoretical computer sciences is a little bit like that. And well, so what kind of processes can you model and have some sense of reality about them? Of course, there are finite processes. So finite processes, you will know about them. Probably you have seen finite automata or some other finite machines, or so you have done some programming. So these are processes that go along some finite path and then they finish. But in fact, if you think of how it is the real life of of our computing systems today, you cannot really say that it is finite. Why can't you say that? Because a finite thing is, well, obviously, in some sense, our computing power is finite, but it's finite with a changing boundary. Every day we have a more and more computing power in this grand system of computing. So this is a very dynamical, fast-growing, finite number. And what is then reasonable to do is to, rather than looking at this finite number, to approximate it by the infinite. So rather than thinking of some, finite, huge number, giga, I don't know what, you say, well, let me just approximate the computing power of the world as some sort of infinite computing power. I don't have a bound. These people do this in applied mathematics, For example, when you do, fluid mechanics, okay? So you look at some behavior of some small object on top of a very deep sea, somewhere in the middle of the ocean. You want to study how a small piece of plastic that is polluting is behaving. So this can be usually described by some differential equation. And what you can assume in this case is that this depth of this water is actually infinite, because it's infinite compared to this small object that you have. And this simplifies calculations while still keeping them very accurate. So this is something like that in computer sciences, that you are interested in looking at infinite processes. And now, what kind of infinity is there? What kind of infinite processes you might look at? So let us think a little bit about what is the infinite. This is a kind of a philosophical question. Many people in many different times had different opinions, but I would say that there are two kinds of infinities that people have considered. Let me just find it. Okay, so this is about what I've been talking about. So you can think of infinity as some sort of limiting process of the finite. So the view that I have given you about what people do in computer sciences using these various machines, Turing machines, automata, all kinds of other objects, is actually kind of the view that people have used in the old times, starting from Aristotle, maybe even before, I don't know, but certainly he talked about this idea of potential infinity. So in potential infinity is sort of a non-existing object, which is the limit of some process. If you think of what you know in calculus analysis, this is all about potential infinity, because we talk about limits and we never include this infinite point. We are dealing with it in a way of just this ever-growing finite. Now, set theory that has already been mentioned, which is the field that I study, made kind of a revolution in this context, because Cantor dared to name the infinity. What do I mean by this? Cantor was a mathematician from the 19th century who discovered set theory by looking at some quite interesting problems in mathematical analysis, actually. So he was looking at Fourier series and trigonometric series, and was wondering at what kind of x a trigonometric series around this x converges. And so he formulated converges uniquely, formulated the notion of the set of uniqueness. And so this is the first time that the set has appeared. For us today, this is, of course, something that we learn maybe in primary school. What's a set? Although the notion of a set is not really precisely defined in mathematics, but we know that this is something about belonging. And once he had this concept in mind, Cantor didn't really work with axioms. He did what we now call naive set theory. So he kind of defined objects without worrying about the logic around, because there was no logic, mathematical logic yet. So he just said, okay, a set is something that can be described by the relation of the belonging, and that led him to look at various sets. He used a characterization of infinity that was already known by Bolzano, which said that two sets are, well, a set is infinite if and only if it's bijective with one of its proper subsets. So this is kind of cool. Clearly not present in the finite sets. And with this definition of the infinity, and with this idea of bijection, you can actually deal with these infinite sets as if they were finite. You can even assign some numbers to them, some sizes. So the size for Cantor was, you take some subset, you look at all the other sets that are bijective with it, you can say that they all have the same size. These days we define it slightly differently because there are some logical constraints to this idea of looking at all sets at the same time, but that's not important for the purpose of this lecture. Okay, so now the next thing that he did is that he showed that there exist infinite sets that are not in bijection with each other. So he showed notably that the set n of natural numbers and the set r of the real numbers are not bijective with each other. So there are two different infinities. Wow. Then he showed even more. He saw if you take this set, any set, and you look at the set of all subsets of this set, then this set does not have a bijection with the original set. So not only that there are two different infinities, but there is a transfinite, as we say, collection of these infinities that there is no way to finish with your infinities, because as soon as you think that there is a biggest infinity, you can make a bigger one by taking the power set. No, just like there is no biggest prime number. So you have kind of a infinite, that's why it's called finite sequence of these infinities. And he tried to really put them in the sequence. So the sequence was, you look at the smallest infinity, which is n. He proved that n is bijective to a subset of any infinite set. So this gives you the smallest infinite size. He called it Aleph 0. And then he said, well, there must be the next. And there are arguments to show that there must be really the next, that this transfinite class of infinite objects has what we call a well-ordered. That is, if you take a non-empty subset, it always has a smallest element. So you can define the notion of a next. So this next one is Aleph 1 and so forth. And so you have this huge number of actual infinity. Why are they actual? Because they are no longer considered as a limit of anything. They just infinite sets, they exist, they must exist because of this power set operation. So they are obtained by something which really is kind of given by an abstract process of taking the power set rather than any sort of limit. And so that led to set theory, actual infinities, and much study that is done in this subject. Now it turns out that after, many now 150 years of this discovery, what turned out is that it is these objects are very real. They are very existing. For me, I'm kind of a Platonist. These objects really exist, and you can study them. But you get further and further from this idea of potential infinity. In fact, for many years, people were puzzled by this connection between finite and infinite. Is there, you take some large infinite number, Aleph 53, is there some connection between the behavior of such a number and behavior of small numbers? For example, you could take a subject that you all know and love, combinathorax. Is there some connection between finite combinathorax and infinite combinathorax? And much has been said on that. I say in a more distant past, because I imagine for you the 70s and so forth are a very distant past. For me, perhaps not the 70s, but the 50s and the 40s, when this was all done, certainly are a distant past. So in that kind of time frame, people studied the infinite and the finite as sort of antipodes of each other. So you have what happens in the you look at all finite sets, what do you know about them? And you look at all infinite sets, what do you know about them? And is there some similarity? And well, so what really happens that there is one big thing about Aleph zero, which helps. It's called the compactness theorem. It can be stated in terms of first order logic, for those of you who know about first order logic. It just says that if you have some theory such that, so a set of sentences of first order logic in some signature, such that every finite subset is satisfied in some model, then the whole thing is satisfied in the model. So this is a big theorem proved by Gödel as a consequence of his completeness theorems. Something that I think you might like to learn about if you don't know already. And it allows you a lot of transfer between finite and the first infinite. So for example, if you look at Ramsey theory, Ramsey's theorem in 1936 is actually about some infinite binary relations, and then he derives the finite Ramsey theorem out of this infinite Ramsey theorem. So there is something we can say about Aleph zero because of this compactness, but this kind of fails for anything else above. So, unless you accept large cardinals, and that's a different lecture, this kind of reasoning is not going to work when you go to the next infinite cardinal, which is called Aleph 1. So people have studied a lot about this. So what happens to the next infinite cardinal for example, with respect to the combinatorics, and most theorems that are known about this show that Aleph 1 is not an object that you can approach through finitistic means, that doesn't reflect the finitistic means, let me say. Let me also say that there is a huge elephant in the room in what I'm telling you right now. That is, we have defined this sort of successor operation between infinite numbers. So we have Aleph 0 and Aleph 1, and Aleph 2 and Aleph 3, and then we get to the limit, take the union, it's Aleph omega, and so forth. But we could also have defined a growing sequence of infinite numbers by using the power set operation directly. So the power set operation directly would go, you take this first infinite set, which is n, then you take the power set of that, which is 2 to the n, called. So this turns out to be the same as the cardinality of the real numbers, and then you keep going. So you go potentially faster than with this success operation. So you have this kind of exponential operation. And the big elephant in the room that I mentioned is that if these two are the same. So Cantor spent a lot of time trying to understand that. That is, if you take Aleph 1, is this the same as the cardinality of the reals? It turns out that this question cannot be answered with the usual axioms of set theory. It's a long story. But there are these two ways of getting the first kind of infinite number, which is not Aleph 0. We call it uncountable. So the uncountable objects, the first one, yes?
Are you still showing this slide with motivation, or did you change it?
No, I'm still showing the slides of the motivation.
Okay.
Yes, thank you. So we are going to go to some more slides, don't worry about it. I think this motivation is important. So now we have this two large infinite numbers that we are going to be concerned in this lecture. The one is Aleph 1, and the other one is the continuum. So now it turns out to connect all these things that I've told you in this very long motivation, that when you look at all objects of size (1), you get nothing. And when you look at all objects of size 2 to the (0), you do not exactly get nothing, but you get a little bit. So there is a little bit you can say about all objects of size 2 to the (0), but not that many. Okay, now let's put all of this together. This is the point of my project. What can we say about those objects which are either of the size (1) or of the size 2 to the (0), but for whom we know their genesis out of finite sets? Now let's stop and think. How in the world are you going to construct an object of size 2 to the (0) by using finite sets? So let's see now back to our motivation, to the first part of this motivation. What kind of the results, sorry, maybe next page. Yes. So what kind of limits you could take in order to get an object of size (1) out of finite things? Or even worse, how could you get an object of size 2 to the (0) out of finite things? Well, it turns out that there are some quite nice tricks to do that. So we are looking at the limit of finite structures, and our idea is, rather than looking at all objects of size (1) that we can get, we look at those objects that we can get as this sort of limit. The same with the continuum. So what are the examples of such limits? So now maybe you have heard of some of these things, maybe not. So Fraser limits are a way of taking a limit of a class of finite structures and get a countable, unique countable limit. Then there are graphones. Graphones made their entry to the world of mathematics in 2006 about these are limits of a sequence of finite graphs which give you a measurable function from the unit square to the unit interval, which behaves as a limit of these finite sets. You can learn about them in a book by Lovash. And this idea had huge consequences because actually it has applications in computer sciences. First of all, it's mathematically beautiful, but it has applications to computer sciences. It has applications to statistics, physics even. And well, there are some ramifications of this called graphings and a very general notion of convergence called first order convergence that is due to Anesha Trill and Patrice Osena. And these things actually turned out to be connected with the notion of ultra products, which is another way of taking limits, which was quite studied in Poland actually in the 50s by Ostowski. And if you look at just the ultra products of finite sets, you actually get huge, interesting objects. And there is something that is a little bit less known called morasses, which perhaps I will say a little bit more about. There are also the construction schemes of Stevo Todorčević. There are many ways of taking limits. And why would we do this? Well, there is something which comes even from directly from computer sciences. It's called data register automata. Well, they are called small infinite sets in the language of Bojanček, who is the one who discovered this. And he came to it using data register automata, so it's kind of cool. So what are the sizes that we get here? We get the first infinite cardinal, number 0, to, for example, Fraser limits, we get the successor, just aleph 1, or we get the exponential, which is the cardinality of the reals, this 2 to aleph 0. And as I said, we don't know. In set theory, we cannot decide by the usual axioms if aleph 1 and 2 to the aleph 0 are the same. So you see that you have this is the problem called the continuum hypothesis. And it's like the P is equal NP problem for set theory. It's a hard problem, which doesn't have, well, which we know that we cannot answer with the usual axioms of set theory. So I have been looking at various combinatorial properties of these sets. So let me show you some results that I have obtained on this with colleagues. So here is the first paper, which is a paper that I wrote with my colleague Ivan Tomasic. So it is published in a Polish journal in Colloquium Mathematicum this year. And what is this paper about? It's about something called the regularity lemma. Perhaps you know this regularity lemma from combinatorics. It's very, very important subject, sorry. It's a very important theorem that was proved by Semeredi, and well, you know, Semeredi got the Abel Prize, and I think this regularity lemma was probably his most important result, because it has, why is it so important, the regularity lemma? Because it has such a huge impact on computer sciences and graph theory, of course. So what it says is that if you have a large graph, you can divide it into some pieces which are kind of regular with respect to some metric. Now, it turns out if these graphs come from a concrete context of fields, finite fields, they are definable over finite fields, as people say, then these graphs are particularly nice. And there is something called the regularity lemma of Terence Tao that he proved to parallel this Semeredi general Semeredi lemma about graphs. And so he got some conclusions back to the context of fields. This is a very important result as well. And the first proof of this result used some rather heavy methods from harmonic analysis, things that spectral analysis and so forth. Well, it turns out that one can prove this type of theorem using this idea of graph forms. And this is what we have done in our paper with Tomasic. So what we did is that we reproved his theorem. So certainly the theorem is his, but we gave a different proof which improved some of the bounds that were known from his theorem and from some subsequent work. And then we used this knowledge to expand to a different context, which is difference polynomials over finite fields. That is over fields with powers of Frobenius. So somewhat technical notion, but doesn't matter if you know the details. It's just to understand that this has some applications. And well, if you want to learn about this paper is available in the Colloquium Mathematicum recently. And it tells you some further directions of research, which I imagine as people who are entering now your further studies, you might like to know about open problems. So there are many open problems in this kind of area. Then let me tell you also about some work which is about to be submitted, although this version that I put on the slide looks like a big mess, but it's about to be submitted. This is a work about big Ramsey degrees. Let me tell you what big Ramsey degrees are. So you all know the notion of Ramsey theorem. You know, the Ramsey theorem says that if you color, for example, the pairs of an infinite set into two colors, then you will have a monochromatic set. And in fact, the number of colors might be whatever you like. If you have 359 colors, there will be still an infinite monochromatic set. So this is great, but now if you tried to generalize this to some structures, so for example, you look at some order, and rather than you coloring pairs, points in this order, and rather than looking at a concrete some infinite set, what you want to do is to have a monochromatic set that is isomorphic to this order. For example, you take the rational numbers Q, you color the pairs, and then you want to look at an infinite set that is isomorphic to Q, but which is monochromatic under your coloring. Well, this is a non-starter. It was proved by Sierpinski in the 30s that this is a non-starter. Actually, independently also proved by Kurepa in 1941. So Sierpinski proved in 1933. Those were the days that the notation, the distance, and the lack of communication meant that you could prove independently theorems with the difference of 8 years. It's difficult to imagine for us today with archive, but these were the days like that. Anyway, so they both proved this theorem, and it says that there is no hope for structural Ramsey theory, as they call it. But then Galvin proved in the 70s that this example that was found by Sierpinski was actually kind of as bad as it gets. So he proved that if you color the pairs of the rationals into any finite number of colors, you will always have a two-chromatic, as we say, subset, isomorphic to the rationals. So this means that the pairs from this subset are colored in no more than two colors. So we say that the Ramsey degree is 2. And this now can be continued. You can study the colorings of n-tuples, of the rationals, and so forth. It's quite a well understood area, and there is kind of a legendary paper about Frese limits by Kekres, Pestov, and Todorcevich, which studied this and connects it with the amenability of groups. Okay, so with my colleagues Dana Bartoshova, Rehana Flatel, and Lynn Sko, what we were interested in is you take an alter product. I don't know if you know what an alter product is. Sorry, I've been talking with very little assumptions on your background, and I hope that this hasn't offended you. I have assumed that there are some undergraduate students that are listening to us, and I would like them to be able to enjoy the talk, even though if they haven't had the chance to hear all these definitions before. So what we proved is the following thing. You take an alter power of finite objects. So this means you have some sequence of finite, let us say linear orders, just to be definite. You take a sequence of linear orders. You might as well, finite. You might take as well, let us say you take isomorphic copies of all possible finite linear orders, and you just enumerate them, 1, 2, 3, etc. So you enumerate them in the order type omega. Now you take a alter filter over omega. An alter filter is kind of a measure with measures sets 0 and 1. The ones who have measure 1 are in the alter filter, and so the alter filter is closed under supersets, under intersections. It contains the whole thing, and it does not contain the empty set. So you take one such thing. Now you can make a product of all of those, Cartesian product of all of those finite sets. And this gives you sequences of finite, of elements of those finite sets. and you say that two sentences, so two sequences are equivalent if the places where they actually are the same belong, the set of such places belongs to the outer field. So you get an outer product. That's the definition. And the outer product of finite sets always has the size of the continuum. And what we were wondering is, imagine if this sequence of finite sets comes from this class, some class whose Ramsey properties you understand. For example, the class of linear orders. We know the Ramsey properties of such a class. So this means for which colorings, how many colors we will get in the mono, how many chromatic sets we will get, you know, in the analog from what I explained to Douglas. So you imagine you start with such a thing, and you would like to have such a theorem also for the outer product. So you want to say, for every coloring of the pairs of the elements of the outer product into, I don't know, 79 colors, there is a 2 chromatic subset. This is your ideal theorem. Well, it turns out that there are counterexamples to what I have just said. You cannot just have such a theorem. You have to restrict your colorings to what we called in this kind of theory internal colorings. So what are internal colorings? So the internal coloring is something that is defined as a sort of limit of colorings on those finite sets. So the coloring of two sequences, Z of, let us say, F and G, is given as something that is definable from the set of all colorings of F of n, G of n, where n is a coordinate. These are internal things. And so what we proved that if we have Ramsey degrees for those finite objects, then we have the same Ramsey degree for these ultra product colorings. So this is, I think, the first time that Ramsey theory has been applied to outer products. And consequently to graphones. I told you the usefulness of graphones. Well, now graphones are a special kind of outer products. So there's a connection between these two papers. So this paper will be in the archive, I think this week, and this paper is available. So this is the kind of results that I have been interested in. And now let's go back to this computer science interest in that. Well, computer scientists are actually quite interested in outer products. And there are quite a number of papers in which they consider some algorithmic properties of the outer product. So that kind of wraps it up for the connection. Let me just take a few more minutes now. We have been so late because of me that I'm not really sure how many minutes I've spent talking, but I just want to tell you a few more things and then I will be done. Just one more thing. So we have spoken now about this exponential
Mirna,
infinity.
you have still 20 minutes. You know, you
it's
started
still 20 minutes.
11:25, so still 20 minutes. Okay.
Oh, this is really great. So I can talk more than about another topic. So these results are, as I say, about this continuum. So how about Aleph 1? Remember, we mentioned this Aleph 1, the first uncountable cardinal. It's kind of a mystery in this context. Because in set theory, we know much about Aleph 1. But kind of negative knowledge in the sense that we have this method of forcing, which is a method of showing that certain things are independent of the usual axioms of set theory. And we are able, through some very nice combinatorial arguments that apply to this forcing technique, to construct weird objects of size Aleph 1. So, you know, you can construct by forcing some object of size Aleph 1, which behaves very, very strangely, like, okay, it's let us see an example of something. It's a object of size Aleph1 that does not embed into any object of size Aleph1 in the universe that you started before this forcing. So whatever embedding you have in mind. So you take a graph, you think of embedding of graphs. So it turns out if you are in a model where CH holds, you can show by classical examples, classical theory of model theory, that there must be a graph of size Aleph1 such that all other graphs of size Aleph1 embed into it. This is just like the random graph. You know, how do you prove the random graph is universal, all other graphs embedded into it? Or finite graphs. Well, this goes through some back and forth argument, which is kind of a forcing this. Some forcing arguments are kind of a version of a back and forth argument. So you can prove that such a thing exists by CH. This is certainly a back and forth argument, and then by some different back and forth argument, you obtain that there are models of set theory where CH fails, and you have a graph of size Aleph1 which does not embed into any graph which used from the family of graphs that you started. So it kind of, this is just an example. It could be a Banach space, it could be a topological space. We have a whole really big collection of knowledge about these objects of size Aleph1 that we know how to construct by forcing. But what I'm trying to put, yes.
So you mentioned Banach spaces, but Banach spaces are always over the field of complex or real numbers, so necessarily they have the cardinality at least continuum, yes?
Thank you for mentioning this. In Banach spaces, you consider the density rather than the cardinality.
Okay, I see.
So these are Banach spaces of density Aleph1. It's a very good comment. Thank you. Okay, so somehow what I like to bring you in mind to have this idea of the non-structure. On Aleph1 we have a non-structure. That means that we have lots of theorems that say that we can obtain weird objects either of size Aleph1 or density Aleph1, as we just mentioned, or some other cardinal characteristics of size Aleph1. If you study topology, there are many cardinal characteristics. So it looks like a non-starter to study nice structures of size Aleph1. What can be nice about structures of size Aleph1? How could we formulate that in sort of basic terms? So, for example, structures of size Aleph1 that have some sort of Ramsey property. We have spoken about Ramsey properties. Can we have such structures? Now it's a kind of a classical theorem, also coming from Sierpinski and his buddies in Warsaw in the 30s, that this is a kind of hard because you can easily construct a coloring of the pairs of Aleph1 into two colors, which doesn't have a monochromatic subset. Or even, as Stevo Todorcevic has shown in a very beautiful and celebrated paper called Pairs of Countable Ordinals, you can have the following. Just listen to this. You take the pairs of omega 1, so Aleph 1, let's say. Okay, you color them into uncountably many colors in such a way that every uncountable subset of the original set, when you look at its pairs, it gets all these Aleph 1 many colors. So this is called rainbow colorings, and it is the diametrical opposite of what happens in Ramsey theorem. So this shows that this alpha is really very different than aleph zero. So with Wierzchow-Kubisch, we wondered about this kind of more modest approach. Why don't we look at only objects of size aleph1, which are constructed in a nice way? So like in this context of the continuum, we have looked at objects that are constructed either through ultra products, graphons, and we obtained some positive theorems. Can we do the same with structures of size aleph1? Is there some way to look at structures of size aleph1 that are constructed somehow nicely, that we know that they're not constructed by some weird forcing and undefinable thing? They are constructed in some nice definable way, which gives them a nice structure. So we thought of this idea of morasses. So let me go to this morasses idea. Now. Oh, sorry that my slides are back and forth, but this is kind of the structure of the talk. Okay, I will go back to this if we have time. Okay, so here is a slide which just shows what kind of things fail for omega-1. So maybe some of these theorems you know, some of them you don't know. But let me just recall. So basically everything fails for aleph1. As I already mentioned, the analog of the compactness theorem fails for the logic, where you're allowed to pump up the definition of a sentence. So you're allowed to take countably many quantifiers and countably many connectives rather than finitely many, respectively. And then you get the total failure of the compactness theorem. So this logic is called L omega 1 omega 1. The Ramsey theorem, I already told you, it fails miserably. Now, some of you have maybe had a chance to look at descriptive set theory. So descriptive set theory is kind of a safer link to the continuum hypothesis. So Cantor proved that if rather than looking at all subsets of the real line, you look at the closed subsets of the real line, then they obey the continuum hypothesis. So any closed subsets of the real line is either countable or it has the size 2 to the aleph 0. So there's nothing between aleph 0 and 2 to the aleph 0. And some other classes also behave in this way, and studying really huge variants of this is the field of descriptive set theory. And if you try to do this type of stuff on 2 to the omega 1, which is kind of, if you think of the real numbers as 2 to the omega, the binary tree with countably many levels, then you get the reals as the limit on the last level. You could try to think of this kind of generalized reals where you look at sequences of length omega 1, and these sequences when converge and you go on the top level, you get the space 2 to the omega 1, and now you try to do descriptive set theory and it's a disaster. Okay, so I'm not going to go into the details, it's very complicated. There is another very well-known theorem about the first infinite cardinal, Koenig's theorem, which says that if you have a tree of infinite height and all levels are finite, there must be an infinite branch. This does not work for omega 1 because you can construct, Aronstein has done this in the 1930s, a tree of height omega 1 in which all levels are countable, but there is no uncountable branch. Okay, so what can we do? Okay, so this is about some automata which I will skip because I think this is a little bit too much. So I'm going to go to this idea of morasses, which I studied with Wierzchow-Kubisch. So rather than looking at all objects of size omega-1, I have now the right to look at only at objects that are built through finite approximations. But how can you build this object of size omega-1 through finite approximations? And it turns out that there is this way of doing it through a Morris, simplified Morris that we took. So the history of this goes to Ronald Jennison, who studied these principles in L, and he studied them in a great generality in order to understand something called two cardinal principles. So he looked at the ways of building objects of size, let us say some cardinal kappa plus n, using approximations of size less than kappa. So that would be called kappa and Morris. And these things exist in L, but do not exist in general. But we are interested only in omega-1 Morrises. So these are Morrises that allow you, so Morrises kind of think of it as some sort of system of approximations. And this system of approximations allows you to build objects of size Aleph-1 using finite things. So that's the notation. And we use actually a simplified framework for this, which was developed by Dan Velleman in the 80s. And what is important about this is that such an object doesn't need any L or any consistency assumption. It just exists in the ordinary set theories, which Fuss is axiomatized by Zermelo-Frankel with choice. So let me show you what this system is. It looks very scary, but it's not really that scary when you read the details. So you imagine that your object is on top of some tower. So the tower is going to be this. This is a tower. And the last one, theta omega, is the object that you're trying to build. And we enumerated using the ordinals, the countable ordinals. And all these other pieces of the tower, theta alpha, are finite positive numbers. And we are trying to build some structure on this last guy. So how do we do that? We would like to build it from the structures that we have on these theta alphas by some functions that are going to induce the structure on omega-1. So these are the functions. So we have a system of functions, and the functions go from theta alpha to theta beta, where this theta alpha could be something finite, and theta beta could be the finite or the last step. And each one of those is a finite set, and it preserves the natural order of the ordinals. And the last one is actually such, if you take any alpha, it's a set of order preserving functions from theta alpha to omega-1, and the union of the images of all the functions is this omega-1. So you need a lot of functions in this last one. Nevertheless, even the functions in the last group are kind of composable. So if you think of this tower theta alpha, you can think of it as lines like that. To climb from alpha to omega, you can break your trip and make a coffee at some middle stage, let us say beta. So if you want to go from alpha to gamma and you feel like taking your coffee break at beta, it's okay, because you can obtain all the functions in alpha gamma as compositions of those functions. And particularly the functions that go from the step alpha to alpha-1 are very simple. There are just two, the identity, and something that we call the splitting function. And there is coherence between these functions. Okay, obviously, there is no point in trying to remember all the details of this definition at the moment, but I want to give you this intuition of building an object on this last level by having some structure on these previous levels. For example, imagine you want to build a graph on the omega-1. So you can build it using the levels that are on these finite steps. So if you have graphs on the finite steps, then your graph on omega-1 is induced by these functions. And well, so our project with Wiesław Kubisz, a Polish mathematician working in the Czech Academy of Sciences, is, and also at the university in Warsaw. We studied this generality of building such objects. This slide gives you all that generality. So we have the finite structures in some language. Look at these just blue points now. Don't have to read everything. So the finite structures with some structure on them, and then we get to build the thing on the top in the same signature. So what can we prove about this? So let us call this class of all the structures. We fix a signature, and we, let us say, graphs or linear order or whatever, and we look at all objects that we can obtain in this way. Call it MK. So K is like this signature or class of finite structures. That's the definition that I have just explained. So the first thing that you might wonder, does this class depend on what Morris you choose? Because nobody tells you that there is a unique Morris. And one theorem that we proved is that this is not the case. So up to isomorphism, you get the same class of structures. So this is kind of nice. And then the next theorem we proved is that this Morris limit is actually a very nice object. So these are some technical theorems that you might or might not know what they mean. But the point of these theorems is that this object of size omega-1 can be actually seen also as a union of countable objects, increasing union of countable objects, and each one of these countable objects can be seen as a Fraser limit. You mentioned, you remember I mentioned that we have a large theory of Fraser limits on the countable, so we know much about them. In particular, they are homogeneous, which means that if you take, I don't know, two finite tuples in this object, then these finite tuples can be put in a structured or preserving bijection, then such a bijection can be extended to an automorphism of the whole thing. So homogeneous objects of size α1 are quite rare. They haven't been studied. And this theorem shows that we have here a factory of producing them through these morasses. So using it, we constructed some homogeneous graphs and something called antimetric space of size α1, which maybe I won't now go into the detail, but it solved an open question. And we have a Ramsey conclusion, which says that if these finite objects that are used in the Morris satisfy some sort of Ramsey degree theorem, then also does this object of size omega-1. And that, I think, is quite a rare thing to have any sort of positive Ramsey theorem about α1. So this is our result. The paper is being written slowly. I guess both Wiesław and I are slow writers, and because we keep putting things in it, but it will come out one of those days. And watch the spot on the archive. I think I'll stop here. I hope this gave you some ideas of how we can approach the large infinite objects through the finite ones and for what purpose we would like to do this. Thank you.
Okay, thank you very much. Are there any questions? Comments? Oh, please, Arthur.
Maybe I would like to ask a question. So, okay, now we know that the continuum hypothesis is independent from the usual axioms of seed theory. Nevertheless, some people believe that somehow this problem is still unsolved, meaning that we should search for some additional axioms which would be in some sense natural and add them to our axiom systems in such a way that this problem finally could be solved. And I would like to know your perspective on this problem. So what is your opinion? Is it right to search for such an additional axioms? I can add also that there was a debate that we should assume that continuum is in fact equal not to Aleph 1 but to Aleph 2. I think it was a debate which was, I don't know whether it was started, but this argument was advocated by Woodin, but somehow then he changed his mind and now he believes that Aleph 1, that continuum should be Aleph 1. So.
Yeah, so thanks, Arthur, for asking this question. Indeed, Woodin is one of the people who believe in this program of that people even call Gödel's program of the continuum, and keep coming with interesting additions to the usual axioms of set theory, which would calculate the value of Aleph 1. As you point out, there are two propositions at least, and in one of them, not of Aleph, sorry, of the continuum in the Aleph hierarchy. So in one of these propositions, the answer is Aleph 1, in the other one, the answer is Aleph 2. To me, philosophically, this means that we are really asking a wrong question here. Because, okay, maybe we find some axiom that resolves the problem of the continuum. I don't think that any of the axioms that have proposed so far qualify anywhere close to be called an axiom, because I think an axiom should be something that a mathematician working outside of set theory should understand and apply and agree if he wants to agree. It shouldn't be something that is only understandable to a very small group of people working on a specific subject in set theory. So we don't have such axioms, in my opinion. And I think, but this is of course just a speculation, I don't think that we are likely to have them. But even if we have them, so what? Gödel's theorem tells us that there is an incompleteness in mathematics. We will have another question that cannot be resolved, and another question that cannot be resolved, and another question that cannot be resolved by axioms. All this idea of being able to capture the whole of mathematics in one axiomatic system, to me, is a very 19th century idea. It was like the time when we felt in the society there is only one civilization and we are going to spread it to everybody else, and the ones who didn't have it before need to be emancipated, or whatever the horrors of the thinking of that time. But in mathematics, really, this is an analog. Can we really capture the whole of mathematics in some axiomatic system? We cannot. The Gödel tells us we cannot. And so, to me, this question is not, I don't see it the same way as those people who are trying to resolve it in this manner. I see it more as now we have all these various universes of the axioms of set theory in which various of these values of the continuum can exist. And we should somehow try to understand the globality of these pluricultural, if you want, universes of set theory. That's what's going to give us the idea of mathematics. I think mathematics is too large to be encompassed by any fixed state of mind.
Okay, thank you very much. And just one more question related to that. So taking a point of view of those people who somehow believe that, okay, we should find an axiom for settling this problem, exactly what is the cardinality of continuum. Do you think that they also have some opinion what should be an answer for a generalized continuum hypothesis, or it is
I believe in this ultimate L that is being studied. This is the one where the continuum should be equal to Aleph 1. So it is kind of a L-like universe, and the axiom is that V is equal to L-like universe, to this L-like universe, the ultimate L. And from what I understand from this theory is that it doesn't answer completely the general continuum hypothesis, but it does give quite a close approximation to it, that is at many stages of the building of the cardinals, we can calculate the value of the power set. That's what I understand, but well, this is a big theory, which not all of it is published, and I certainly wouldn't say that I am the specialist in it. I just can say what I understand of it from what I've read.
Well, okay, thank you very much.
You're welcome.
Okay, are there any other questions, comments in the audience here? No, and maybe on Zoom? Does anyone on Zoom would like to ask a question? Okay, it seems that nobody. So let's thank Mirna again.
Thank you. Thank you very much, and thank you for being patient with my problems this morning. I'm really sorry about that, and I'm sorry to be cutting into your lunch break, probably.
No, it's not a problem. We still have like 20 minutes.
Okay.